So welcome everyone to the microstructure tutorial. Imagine everyone's likely pretty fried already by this point in the week. So thanks for being here. So I'm Mike Durand. I'm at Ohio State. I'm presenting, but just want to kind of acknowledge all the people that have contributed to this, including Micah, HP, Tate, Megan, and Scott. So thanks to everyone. A lot of the database work, draws heavily on what Micah presented earlier. So today, goal for the end is to be able to explain why microstructure is important for remote sensing. Might seem counterintuitive at first. Define different ways to measure, quantify snow microstructure, especially specific surface area, and then access and visualize 3 different microstructure data sets from SnowEx Grand Mesa 2020, and then some of those will be easily transferable to other SnowEx data sets as well. I wanted to give one caveat right up front, which is that 2 of the 3 data sets we're looking at are published at NSIDC, whereas the 3rd, specifically the micro CT data, is on its way there. It's getting published, but what we're working with is kind of a preliminary version. So the providers asked me to just give Lauren Farnsworth email here. So if you have questions on the CT data, she's the one to go to. And should also just mention that this data took tons and tons of people hours to collect. So thanks to everyone who's actually measuring. Things about snow microstructure. So why is it important? Snow microstructure actually plays a really important role, both in snow physics, which I'll talk a little less about, but also in snow remote sensing. So actually a lot of effort went towards measuring it last year. There's a number of different quantities that people use to try to measure or characterize snow microstructure, including grain size. It's actually hard to make grain size measurements with a hand lens in an entirely repeatable way, especially across observers. And they're also a little bit challenging to relate to what we're interested in remote sensing. So there's been a lot of work in, say, the last 15 or 20 years to make more objective measurements of snow microstructure, though I will say that work does extend all the way back to the 80s. But there's been a lot of progress lately. So why do we care? Snow microstructure actually controls a lot about how remote sensing measurements end up looking. So for example, here's a figure from one of a review paper that Jeff Dozier led. And there's different ways, different things to look at here. Look at maybe just the middle panel here. So what we're showing across the x-axis is wavelength. So this is a spectral plot. And across the y is snow reflectance. The units are microns, so visible light's way over here on the left. The different curves, you can kind of ignore the red line for the other red line for now. The 4 different curves here, starting from blue and going down to black, are fine versus coarse snow. And so for fine textured snow, so a kind of a smaller grain size, if you want to use that term for now, you have a lot more reflectance. Then as that grain size gets larger, there's less and less reflectance, especially in certain parts of the spectrum where you have absorption lines. So here's the ice absorption coefficient, which kind of anchors these calculations from a first principles point of view. You can see there's a huge difference across these in certain places. It can make a huge difference at how reflective snow is. That's visible near infrared. And you get a similar dynamic with radar. So SWISAR style radar, so that kind of higher frequency KU band. And in that context, these are 3 different single scatter albedos, which are able to relate to grain size. You can see that the backscattered microwave radiation also is a pretty large function of the grain size. So it's really important to interpret these. interpret remote sensing, which is kind of funny when you think about it, right? Tiny, tiny structures the size of millimeters ends up affecting what you see from like space, right? Across meters and tens of meters up to kilometers. A big area is figuring out how to use information from Snow Microstructure to inform possible snow water equivalent retrievals. So microstructure itself varies a lot over the season. It varies a lot with depth. And it's the evolution of it is controlled by other snow properties. So snow temperature gradients, vertically, snow height, snow liquid water content. And if you're interested in more about this, there's a couple of recorded talks by Kelly Elder, who was here a minute ago, he might still be here, that were part of, I think, this year's SnowEx training materials. And so HP shared those links, so check those out if you're interested. So any questions or comments or anything before we kind of dive into the measurement techniques from SnowEx? Just like interrupt anytime.
Mike, just a clarification that your plot there is for different grain sizes, assuming spheres.
Where? Yeah, this one is, I believe, radiative transfer calculations that assume spheres. Okay. Yeah.
And the KU is as well, probably the backscatter part.
This is a little dodgier. This quantity is a single scatter albedo is what's shown there. So that's what those numbers mean. And this is based on like a super simple thing from Ulaby. I couldn't find a perfect graphic to illustrate this. And so I just did one from a kind of
that's great.
Yeah.
Thank you.
So it's a good segue. So one of the measures or the quantities we talk a lot about in microstructure is specific surface area. And specific surface area, or SSA is the acronym we'll use, is a very common quantity in a lot of materials to describe different kinds of material properties. It's not like just specific to snow that we're interested in it, for example. It also is not the only quantity that could be of value to know about. So I have like a list of a bunch of other quantities a little bit below. And here's a couple references. Sorry, this isn't the Jupyter Hub view, so the references all look funky, but if you kind of look at it on the on the website, they all render nice, and they'll hyperlink you to those okay. So specific surface area is a quantity that is, you can imagine it as like all right, let's see what happens. All right, just gonna stay here. I don't know what's, okay. It's gonna be annoying. How about if I finish? I don't know why it didn't let me restart.
This might be just a temporary glitch. We had that yesterday as well, so it might come back soon, that server.
Okay, I'll just carry on for now.
Scott was saying the refresh button up in the browser search thing would also help. Yeah.
There.
Yeah.
So I was trying to reload it and it wasn't. It bombed out. So I'm just gonna finish the part that we don't need any. I'll just keep going with this part since it's maybe switched to here so we don't keep getting that. Okay. So what is specific surface area? So you can imagine it by looking at these graphics that show micro CT representations of snow. And just imagine all of the surface area of the ice structure, the ice air contact. Imagine all that area and then normalize it by something. And we'll, that's where the specific comes from. And unfortunately, it's defined a couple different ways, and I'll talk about that in a second. One of the ways that people often do is to normalize it by the mass of that sample. So you have a square meter per kilogram. Okay, so imagine the mass of each of these little cubes, the surface area of those cubes, and then SSA is just the square meters per kilogram. So the SSA varies from, say, I don't know, you can imagine values outside this, but a low value would be like 5 square meters per kilogram, corresponding to this coarse grain snow, and then 150 meters per square meters per kilogram for this fine grain snow. It takes a little while to get used to those values. So often what people do is talk about an equivalent diameter. And so I like talking about a spherical equivalent diameter, and we can kind of go down the rabbit trail of the different ways people describe this quantity, but it's essentially just transforming that value directly into what the SSA would be, or what the diameter would be if for a sphere with that SSA. So it doesn't, you're not making any assumptions. You're not assuming that the snow has spheres at this point. It's just a transformation of the SSA to a different quantity. And this is the, again, if you get confused, what is SSA? The surface area of ice area interface divided by the mass of the ice. And then with this single equation, you can just transform that into an equivalent diameter that's a little bit easier to sort of interpret conceptually, at least for me. Like I can remember what 1 millimeter versus 0.5 millimeter sphere grain diameter is easier than the square meters per kilogram values. And I'm going to skip some of these contextual notes. These are some of the other quantities that people talk about, and so you might be interested in checking some of those out. But I thought I would stop for another second and see if anyone's got other questions or comments before I try to restart here. Awesome. Megan was right.
I have a quick question, Mike.
Mhm.
Are you going to explain how SSA was measured in SnowEx? I guess that's what you're pulling up now, right?
Yeah, that's what I'm doing next. Okay, so instruments. We're going to talk about 3. So the first is micro-CT, which stands for microcomputed topography, tomography, I'm sorry. And Lauren Farnsworth from Krell was making those measurements. Here's Lauren. So she would literally extract small samples of the snow, put them in a padded and special cooler that kept them cold, and then transport them back, keeping them cold, to the lab. And here's the CT machine itself. I think you can just see a little hint of the snow sample in there. And there's various ways that this is done. Sometimes you cast it, sometimes you just ship it back cold. So that's micro CT. And what you get from the CT machine is literally an X-ray that tells you within that sample, each few nanometers, whether you're looking at ice or air. It's just like you can think of it as a 3D ice air classification map for like a several centimeter sample of snow. So that's one of the 3. The second we'll talk about integrating spheres. So an integrating sphere, measurements were made by actually 5 or 6 different people at Grand Mesa. This is Kihan Yang from Colorado. And this was our instrument. And what she does is take a small sample, which you can see in this little black cup, and then you insert it up into this little white box. And inside that white box, there's a little spherical space. The snow is shot with lasers, and then you measure how much reflects back into a sensor. And then you can measure that you can relate that reflectance value back to specific surface area. So we had 3 different instruments actually out there. This was our ice cube. Then there was another ice cube unit, which is like ice cube is a commercial version of this sold by A2 Photonics. And there's also a sort of homemade one by the University of Sherbrooke that was out there as well. So there's some more background on that. And then the third method to measure was SMP, Snow Micropenetrometers. And those are also a field-based approach. So similar to ice cube, which is a field-based, but they do not require a snow pit, and thus are amazing because you can get way more spatial coverage. The idea is that there's this, here's Megan Mason, who is the lead for all of those measurements at SnowEx 20 Grand Mesa. So there's this long pole that literally is pushed with a motor down vertically through the snowpack. And there's a sensor on the tip that measures literally the force it requires to break the snow grain bonds as it goes down vertically through. I've probably butchered that, Megan, but that's my simple way I think about it. Of the three, the SMP is like the least, related. SMP is a very robust and fascinating thing, and it gives you a wealth of information, but relating it to specific surface area is not necessarily super mature. And there's just a couple papers out on it. Ice Cube is sort of intermediate. It's been around for a while, but there's some issues with it. CT is typically thought of as your gold standard, though there's always caveats with all three of these. All right. Questions here before we start working with data?
Hi, Michael. I was just checking to see, so is the SSA like a measure of porosity in between the grains of snow? Is that kind of the concept behind that?
No. So the porosity is directly related to density.
Mm-hmm.
The specific surface area it's literally this quantity that tells you the surface area of the ice air interface normalized by the mass. And it's a measure of, for lack of a better, the size of the snow grains. If you look at like A versus B, you could almost imagine a case in which, though it would be unusual, you'd have fine grains that had the same density, the same bulk density for that sample, but would have different SSA, different sizes of the grains. Does that help? I know it's a confusing quantity.
Yeah, I kind of get what you're saying. Yeah, I see what you mean. Okay, thank you.
Yep.
I've got a question about the SMP.
Yeah.
So I know you cited a couple papers here that I should dig into, but do you mind explaining how, just conceptually, you go from a force to or a density, or what the guiding principle is there?
Yeah. I was always skeptical myself because it's harder to imagine how it works. But if you think about things, and there, especially if you have softer snow, it might be easier to push through. If you have more densified snow, it might be harder. There's also places where this doesn't work, which I've always kind of poked them on. Some of the folks that developed this, like if you have a really weak layer, it might have large grains and low SSA, but be easy to push through. So I think those SSA versus force relationships are best done with local calibration. And that's how we'd always sort of imagine this. And so our kind of plan for including SMP was to calibrate it against the integrating spheres. Should also mention one other thing, which was that we had about 10, a little bit less than 10 snow pits where we have micro CT data. We have about 100 snow pits where we had integrating spheres, so only those vertical profiles, and there's 100, and then something like 1,000 SMP profiles arranged around the pit in like a cross pattern, which you'll see here soon. The idea is to kind of calibrate it locally. It's been shown empirically to relate.
Okay, thanks.
Yeah.
I have one last question for you. Does this work in wet and dry snowpacks, or is it mostly just dry snowpacks?
Better in dry.
Okay.
Yeah. I think the integrating sphere is the one I'm the most familiar with of these. That one is not set up to handle wet snow in the relationship between reflectance and SSA. It's not. The CT data cannot handle wet snow because you have to freeze the sample. The SMP, I don't know, but I would think it would be complicated. Megan, you got any
Yeah,
guidance for us
the
on that?
SMP could definitely take measurements in dense, wet snow, but you might not get a lot of them right in a row. And if there were like an ice layer, then that wouldn't work too well either. Or
Would
or
you-
if a wind slab is too hard too.
But beyond that, would you be able to relate the force to the SSA in the context of wet snow for SMP?
I'm guessing that's not very mature yet either.
Yeah, I haven't seen anything on that.
Yeah, I
So
think a
along
lot of
those
it
lines-
comes, I was just gonna say, I think a lot of it comes back to how many snow types have been empirically, compared with
Mhm.
micro CT and SMP.
What about ice lenses on the micro pen?
Yeah, it can be hard to get through the ice lenses. There are 2 separate force sensors on the SMP, something to be aware of. The larger force sensor allows you to get up to about 250 newtons of penetration force, and the smaller one is about 40 newtons. And you can tell almost from the data which one you have, because the larger one has about 10 times lower force resolution. So you can put a stronger force sensor in there, but then you lose resolution, and some of these microstructure estimates are not as good. So it's a trade-off. We normally use the 40 Newton one,
Thank
and
you.
don't worry about ice lenses.
Yeah, and also on ice lenses, usually the instrument kicks back, so your measurement gets a bit like forced on that because the ice is just too hard to penetrate.
Yeah. Okay, so I'm gonna keep on rolling. So let's get into our working with the data part. So we're going to do 3 different things. And so because it's 3, I'd encourage you to follow along, but I'll move along quickly because I think we have about 20 minutes. So first we're going to intercompare the 3 different units of integrating sphere that we had out there. Second, we're going to compare integrating sphere SMP and CT at one pit where we had all of the present. So as always, we'll start by loading libraries, loading modules. Sorry, I'm kind of a Python newbie. So we're pulling in the SnowEx SQL database. And some good things like GeoPandas that we need to work with the data. So there's 3 different integrating spheres, and a shout, just a kind of reminder, this data is published. There were 3 different ones operated by a number of different people. So if you run into issues, so I was kind of the contact for these. So I'm happy to talk with y'all, or you can go back to the operators. All that data is logged in the data files. So the SSA, or the integrating sphere data, is all in the database, which is really nice. So you can pull all of it just with the layer data type equals specific surface area. And then yank that into a data frame, and following Micah's examples from his tutorial. So this is also his snippets here, a lot of it. So I won't spend much time on that since that's already kind of been gone over, but you can see the data frame, including which instrument. So this just showed the first 5, and these are all from the IRIS instrument, which is the University of Sherbrooke one. We've got times and then metadata, as well as the specific surface area itself over here in value. Okay. So this little bit, this cell here, grabs all of the sites, so all of the snow pits, you can think of it, that have more than one instrument. And so it loops over. You can kind of, I guess I won't talk through what it's doing in any detail, but it's just going and saying how many of these actually have more than one instrument. And then it will tell you, then I'm just returning the array of instruments. So one of them is the iris, and then these two are the ice cubes. The one that ends in F is the Finnish one, and the one that ends in US is the OSU one. All right, and then finally, this is just a typical thing to plot the data, and we'll end up popping those up. So the font size a little small. Sorry about that. So we see 4 different plots here. Each one's a different site. And the 3 different lines are always the same. So black is the iris, the pink is, or magenta is the Finnish one, and then the cyan is the US OSU one. And these instruments are very similar. Even the iris one uses a similar, the sphere itself is very similar to the one used by the commercial unit, as I understand. So it's not too surprising, perhaps, that they're consistent. Remember that they are all, because I would say they are fairly consistent throughout. And I'll make a comment about the top layers here in a second. But they are all pulled from slightly different snow samples, right? So these aren't the same exact samples. They're from a different spot on the snow pit base. They're also done by different people. So any slight differences in how people do sample preparation and other things could influence these. So we were pretty happy about the agreement. And you'll see the agreement's considerably worse at the top layers. There's a couple going on there. First, it's hard to prepare samples with fresh snow, and I can talk more about that if you're interested. And second, the curve is a little bit steep there, if it makes sense in the relationship. So basically a little bit of noise and reflectance can lead to more noise in the final SSA. So I tend to not be too concerned because I'm interested in the microwave response mostly. And so this stuff to microwave is all fresh. It's like 70, 50, 30 SSA, it's all the same. It's all like fine grained snow that the radar is gonna more or less see through until you get to these lower values. Okay, so that's the first of the exercises. Any comments or questions about that? Okay, so next we're gonna pull the SMP data and compute the SSA. And so there's a few things to mention here. Megan, again, who you all know by now, is the contact for this data. It's up on the NSIDC. If you use a profile, you might consider checking out this Excel sheet. If you want to use this data, check out this Excel sheet, which is also on the NSIDC. And it's like for all like almost 1,000 profiles, it's like any notes, any comments that are like, oh, I didn't get through this hard layer for this profile, anything like that is all logged there. So the couple things, the SMP data is not 100% of it is not in the database. Instead, what was done, because there's just a lot of it, it's a lot of samples per centimeter of vertical profile, and then there's a lot of vertical profiles. So it was kind of bogging the database down. So what Micah did was downsample it to 1 out of every 100 vertical samples in the vertical profile are included. So there's some for every single profile, but the vertical profiles themselves are incomplete. And that actually is a problem because the software that converts that to SSA doesn't just have a relationship between instantaneous force. It's like, and it's not just a average. My understanding is it's kind of like a, it's taking the derivative, it's sort of smoothing and then takes the derivative of that force and other things. So you need it all there to get the SSA. But it's still useful because you can visualize where the SMP profiles are and decide which one you need. So we're going to use the database to do that. So here we're going to pull all of the layer data type equals force, which is how you can filter things out by SMP. And we're also going to choose a single site. Here we're going to use 2N13, which is the one where we have all of these. And then we do the database query, convert that to a data frame. And then we also need to get the snow pit for there. And so to get the snow pit, what I did was just grab the layer data type equals hand hardness so that I could get the snow pit location. So that's kind of, there likely was an easier way to do that. Then we're gonna plot spatially the location of the snow pit and the location where all of the SMP data measurements were taken. And so here we've got easting and northing. So this is a map, right? And then here's the snow pit, the big black square. And then the triangles are color coded based on, I believe, when they were taken, acquisition order. So if we want to compare them, we'd probably want to grab the ones that were close to the snow pit. And in fact, the measurement protocol, which Megan can clarify if I get wrong, was to measure just behind the snow pit face. So there were several that were made just behind the snow pit face to enable this kind of calibration and comparison. Thanks for the thumbs up. And then in addition, to make measurements along these two axes, this cross, which we've called a King's cross since Josh King came up with the sampling protocol for work in Trail Valley Creek. So we want to get those ones that are right by the snow pit to try to eliminate the possibility that any differences are just due to spatial variability. So in order to do that, what we're going to do is just calculate the distance from each of those SMP vertical profiles to the pit location. And then return the sorted, as a data frame, the sorted values. So what this is showing here, this is what we're actually going to use in the next step. So this one kind of matters. These are like IDs. On the column on the right is the distance between the SMP location and the pit location. And then over here is the actual sort of raw file name. So the idea of the closest profile is actually 1174. And so again, like I mentioned, you need the full resolution data. So I went to the SMP page on NSIDC, which I can go there if you want. You can go through the steps to download that, to download a data. But if you just search 1174 in the SMP page, it'll pop up the right one. You download it, and then that file's been made part of our tutorial. Okay, so now we need to compute SSA from this. So for this, we're going to use the Snow Micropin modules that were created by Swiss, the SLF group, to show you maybe familiar with. You can read more about here. This is the read the docs page. There's some issues where things are a little out of date on Python versions, as it hasn't been updated in the last few years. And then there's a big caveat that I need to say here, which is that this tutorial uses this Proksch 15, Martin Proksch 2015 paper to relate SSA to the force. And as it turns out, I'm going to show that, but as it turns out, a paper came out last year that shows that this is not truly applicable to the version of SMP that was used. And I've got some comments on that later. All right, so this imports the Snow Micropin. This pulls in, it downloads from the AWS bucket, the S3 bucket, the files that I said I downloaded. This PNT is the force profile. So you can download, by the way, the CSVs as well, but this package won't, I don't think, know how to parse them. You need the PNT data. Okay, and then this just, these lines just loads in and plots the force as a function of depth. The final step is the SSA calculation. And here we're gonna run that. And so this Proksch 2015.calc calls the library, the Snow Micropin library, applies that empirical relationship. And then here I'm just displaying the first few SSA values. Okay, and I have more comments when we compare them on the correct library to use, which I can talk about in a few moments. Any comments on all that? Okay.
Do you know what method they use to find the coefficients?
Yeah, I don't. So the thing is the hardware. So Martin Proch from Proch 15 was using an old version, I think, of the like SMP controller version 2. And this version that was used in SnowEx last year was version 4. So there's another paper that's cited down here in a minute that by Nej Cologne that redoes things like evaluates this relationship with the version 4 controller, shows it doesn't hold very well, and then recomputes new coefficients. So it's like there's something about the way the actual physical hardware was done that you want to use the newer one.
So I guess that's just one thing to keep in mind, just that it's a totally empirical relationship.
Yep.
And so you want to believe this over the range of samples that it was tuned to. And when you get outside of that, we probably have low confidence.
Right. And that's why I think for our project, I'm pretty sure what we're going to do is tune it for this data. But we have a meeting afterwards to figure it out, which is a good reminder. We should wrap up so we have time for our meeting. Okay, let's see. So let's move on to the CT. So the CT data is not up yet. I mentioned that. So I have received from Lauren Farnsworth a subset of the CT data for only, well, what's shared on the Jupyter Hub right now is only for 2N13. I have 4 more snow pits that I can share as well that the microstructure project is working with. I wrote a Python function to read that format, and don't look at it because I'm a Python newbie, so don't judge. But anyway, it works, and I was able to verify. I verified with an Excel sheet that Lauren had that these are coming through okay. I want to just mention and highlight, I'm not going to go there because of time, but the data, the files themselves, or I think I can see. I think I can do it real quick. So this part may be a little trickier to follow along. But the data files themselves have just an absolute wealth of information in them. So if you just check one out, it literally, the software identifies object by object, and then creates structural metrics for each of those objects. So like every place there's a distinct blob that looks like ice versus air. And then it creates a ton of interesting and potentially very useful microstructure parameters that, and then of all this, so far, we're just grabbing this one, the surface area to volume ratio, which has to be computed to the metric we use. So I just wanted to highlight that there's tons of information in here. For this tutorial, I'm just looking at the specific surface area. So now we're gonna plot all of them up. And this is what we get. So here we see the black and the cyan are the 2 integrating spheres. You can see that they're still consistent like I showed in the previous graph. The dark blue is the CT. And that one was a surprise. I mean, I saw this for the first time a week ago, 2 weeks ago. So I was a little surprised at how much divergence there was between the CT and the integrating spheres. So that's something that we're going to be looking at. The orange is the SMP, and there is a reason that this one is so far off, because this is considerably more off than the others that compared to the sort of consensus between the other 3. And like I mentioned, paper came out last year that shows that, again, you need to use a different set of coefficients for this particular SMP hardware. So Mel Sandels, who's here as part of SnowEx, has a fork of Snow Micropin repository that has coded those Cologne coefficients. And so that's what we're using in our microstructure, in the microstructure project. So if you're interested in taking this forward, let me know. I do have a plan to update this tutorial afterwards with sort of the latest. Yeah, so I think to wrap, it was sort of a downer for me when I was like, oh, there's these huge differences between these different properties and measured in these different ways. But hey, that's science, and we're going to learn something and dig till we get to the bottom of what's going on. And when we get there, it'll be interesting, right? And that'll help inform future things. There's the last thing I was going to say is that there's a number of interesting things you could do to compare these. One of the things you might do is compare it to the SWISAR radar data. However, I'd love to talk to you about that if you're planning to do it. There's more things going on there than you might think. And one issue with the SWISAR is it does have these orthorectification issues. So it might be off by about 100 meters or so with where the lat long or the XY coordinates show it. And then there's also this annoying thing about this relationship, which is that, right, if you have a shallow snowpack, you might have a larger snow grain, and vice versa, because of the temperature gradient is part of what drives the vapor flux, which then drives the grain growth in certain contexts. And so grain size and depth push the radar in opposite ways. They're inversely correlated, so you might have the same radar response for a shallow and deep because of the ways that those things co-vary. Anyway, and then finally, my group has done a little work with the integrating sphere work and just shown that there's the SSA is actually fairly consistent across Grand Mesa, taking some of those things into account. Yeah, so our project, I'm pretty sure what we're going to do is calibrate the SMP and develop a SnowEx 2020 Grand Mesa set of coefficients. And that will let us have SSA for every single SMP profile, which I'm really excited about. So I think we're almost out of time. What comments or questions?
Mike, could you scroll back up to the plot right above there? I think, like, does it seem like there could be some depth stretching? You know how, depending how these depths are measured, sometimes your profiles can kind of accordion, and clearly the amplitudes are way off here, but I think if you shift some of that, there is maybe some agreement in the shape, maybe.
Yeah, Mike,
there's a lot of
maybe just related to that. Did you pick the snow surface in the SMP first?
Maybe not.
Because the SMP goes through air for a bit, right, until it hits the surface. So the
Okay.
The first step would be to look at that raw force profile and look for that first increase above the sort of background noise floor, which is usually around 100th of a newton.
I don't think I understood that. So I'd assumed that the force profiles started at the snow.
No, it starts
But
when
I'm not
the instrument
sure.
starts measuring. Yeah.
But I've also grabbed, so that's really great. So I've also grabbed Micah's snippets that pull in the SMP. So it's possible, depending on what you did, Micah, you may have done that, but I didn't make any adjustment for that. So that may be part of what's going on.
It could have happened within the Snow Micropine library. I don't know if that automatically picks the surface or not. It might not, because that's usually something that's done manually. Yeah.
Okay.
I'm sorry,
so
Mike.
How would you automate that over all of?
When I pointed you to that Excel, that was point number B. Yes, the air part.
Got it. I missed it. So
nice
in
job,
this
Mike.
one,
thank you.
Maybe you'd expect. Okay. Yeah.
No, go ahead. Go ahead.
Yeah, I guess. Yeah. So the way to do it is to go to the Excel sheet, and then you've got a height or something in there that. Well, anyway, we can talk offline.
Not quite, but yeah.
Cool. What else?
Our group wanted to use the SMP and now I'm scared. Can we elaborate, like where is the top of the snow and the bottom of the snow in the SMP? It does look like it's just stretched super weird here.
Yes,
Well,
it seems like there's a few things to track down. The output of that Snow Micropen would be good to verify if that's distance in air. Like when it comes out of the raw force profile, it's just distance as that, force sensor was moving from when it started. So if you want to do it from height above the snow interface, you'd want to pick the ground, which most of these SMPs did go to the ground, which is obvious in that force profile as well. But hopefully that's not the, I mean, looks like if you had to flip this, it would be even a worse agreement. So hopefully that's not the case.
Yeah, I mean that, yeah, I don't think it's flipped.
So in the published data set right now, it's essentially submitted as raw data, and it is it's been cleaned out for like complete outliers, and those were removed, but there was no algorithms that went through and started it at the surface. So that would be like the best thing to do for a level 1 data set. And that was not done for this submission. I think the best right now would be plotting it, and then it would be very, like I say, very obvious, but it would be a very different force when it goes through air versus when it hits the snow.
So Megan, does this one have like a really hard crust? Is it like air, 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 and then at 120, that's crust?
Yeah, that's how I would read that.
Okay.
Can I comment on that? So under the profile function that you call, there's that you can do the profile detect ground and detect surface. It would be interesting to compare where you think the surface and ground are from that profile and compare that with the auto picks from that function.
Got it. Yeah, I have not tried that. So it's just like P detect or something.
Yeah, there you go. Detect ground. And yeah,
okay.
that.
Ah,
Nice. So maybe it already has
Nice.
been done automatically.
But heading says it's a bit dodgy. It was heading says it's dodgy. So there's as part of the Snow Micropin package, there's a pin GUI, which so it's a GUI that you can like manually identify the surface and ground, and then when you then it creates a .ini file, and then when you later try to use the .pnt file with the profile function there, it will search for that .ini file and then pull in the auto picks, sorry, the picks that you've done. But I've never got the pin GUI to work, so let's see what happens.
Yeah, if you can't get that to work, you could just zoom in on your Python plot here, and it's usually fairly obvious where you go from a consistent kind of just noise in the air, and then you'll see it step up when it. The tricky ones to pick are when it's like really low density fresh snow, right? Because sometimes it'll bump up just barely above the noise floor.
so like squinting at this one, it looks like there's a tiny little bump there.
Yeah.
And it grabbed the detect surface, grabbed that one, 189. So it's on the left of this.
So it'd be worth looking at the snow pit stratigraphy and kind of seeing how things line up there too. It can help you take a look at where to pick the surface in this data.